Okay, well, welcome everybody to the International Genetic Solutions Symposium. What a great crowd. We're very excited to be a part of this, excited that you all could join us. And I, for one, feel really fortunate to be a part of this collaboration. What an awesome job for everybody in this group to have open minds and instead of feeling like competitors, be allies with one another. I really am honored and feel fortunate to be a part of that kind of philosophy. Today we have a packed schedule for the next 2 hours or hour and a half, starting with Dr. Bruce Golden and then a panel discussion with several of the EVPs from the various IGS associations and some breeders affiliated with those associations. So we're just going to jump right into it. Dr. Bruce Golden is a co-founder of Theta Solutions, which specializes in the development of analytical methods and software of genetic and genomic data. Dr. Golden, prior to that, was the department head of the dairy science department at Cal Poly. He also was the co-founder of and CEO of Optibran, a livestock and pet technology company. Dr. Golden was also a member of the faculty with Colorado State for 19 years. Goes without saying that he's had a really large footprint in the area of animal breeding and genetics. And I'll say I came to work for the ASA about 3 years ago. And soon after I came to work there, I was able to watch Wade light up when he found out that Bruce Golden was going to get involved in kind of rethinking, rejuvenating, remodeling how we do genetic evaluation. And so Bruce worked with the researchers at Iowa State, Dorian Garrick, Mati Sachi, and others there, and the ASA and the IGS partners to rethink how we are doing genetic evaluation. And without Bruce, we couldn't have made the progress that we are making. So everybody in this room is going to be a beneficiary of Dr. Golden's work. So with that, we'll turn it over to Dr. Golden.
Okay, so I'm going to talk about a little perspective. I'm going to talk about the company, just so you know what we're trying to accomplish. There's nothing nefarious here at all. Talk about the software that we've developed, and specifically some aspects of how we accomplish what we've accomplished, and then give you an update on the IGS analysis. By way of perspectives, I always like to start by talking about why we're doing what we're doing here. What motivates this? You know, we've had this evolution over the last, 50 years more of models and an analytical technique all involved in predicting genetic merit of livestock. And this is just kind of a highlighted list of the things that we've all gone through, that specifically ASA has gone through over iterations. So I just want you to understand that what we're doing now is, I consider, a technological leap forward, but it really is just part of this evolution. And this evolution, I always feel like it's motivated by something very special and very specific. So think about it. What drives this? I know a lot of you have seen me talk and give variations on this talk before, and so I know you know the answer, so shout it out. You know, we have a change in knowledge of models over time. A lot of smart guys working that I get to work with and others have changed the analytical models. They've become more sophisticated. We've had a lot of change in methods over time, but I don't think these are the kinds of things that are driving this change, what's motivating it. We've had a lot of change in data, and now we have a huge change in data. This is the largest multi-breed data set I've ever seen, where we're joining, what are we at now, 12 different associations representing 8 breeds? Do I have that right? 6 breeds? Something like that. And a lot of other crossbred data in this in a single space. And that gives us some really unique opportunities to do things, but I'm not sure that's really what's motivating why we're doing what we're doing. It certainly is a big factor. And then we've also seen all this evolution and enabling computer technology, and you're all generally aware of what's happened, of course, in computing. All you have to do is look at your PDA or your cell phone or whatever you've got in your pocket these days. Really what's motivating it, in my mind, is this quest for making predictions more accurate, for identifying more accurately the animals we want to make selection decisions on, because that's one of the keys, if not the key at this point, to making genetic change, to making genetic improvement. And so specifically, we want accuracy, high accuracy on young animals, the new animals that we want to select from to enter the population in order to make this genetic change. It reduces generation interval. It makes our selection progress just faster toward what we need to do. So with that in mind, a few years ago, gosh, it's been almost 3 years ago now, Dorian and I specifically, we've worked together for a long, long time. I think Dorian and I have been working together in this area for 25 years. We've published together. We've spent a lot of time. We vacationed together. And we've written grants together to fund software development. And that well is pretty well dried up. At best, it was always pretty iffy, and it's hard to get the breed association. No one ever overestimated the cost of software development. It's pretty hard for the breed associations to actually cover that cost by themselves independently. And we decided to try a new model. Form a company, form an LLC. It's just the two of us right now. We're looking to expand. And license software out to breed associations, to breed organizations, to companies, to government labs, and not even just within the livestock space. We're looking at plant genomics and even human space for the software licensing. We think that this will be a more, so far it's proven to be, we think this will be a more sustainable kind of model. Our goal is not to get rich, although that'd be really nice. That's really not our goal, I know. It's to have a more sustainable, viable model for the next generation of genetic evaluation methods and software, because the level of sophistication has increased at an increasing rate. It's harder and harder to do these analyses, especially now with genomic information, and to do them right, to do them well, and to get the maximum value out of the very expensive investment being made in genomics. And everyone knows what the cost of a genomic test is. And right now we've got, I think my latest run this weekend was 46,000 animals genotyped in the prototype analysis. Well, that represents a very large investment. So we want the analytical methods to be able to get the maximum value. We also realize that not everyone has access to huge supercomputers, especially for regular production runs. So we looked at a different kind of approach to doing this. And this isn't an approach we invented. This is an approach in computation that's being used in a lot of other disciplines. Specifically, this approach is being used in all kinds of sciences and financial analysis. And this is to leverage the technology built for gaming computers. Because if you've been following the gaming industry at all, it's tens of billions of dollars annually spent on these things. And the secret to the gaming industry, computer gaming industry, is this development of what are called graphics processing units. And these were designed to draw the pictures for games in real time very quickly. Well, scientists realized very quickly on that that's just math, and we could apply this to other analytical processes, and they're very inexpensive. You can buy this hardware much, much cheaper than you can get a supercomputer. And there's then a lot of other hardware components that came along with it that accelerate the computing effort. So we focused developing our software in that kind of environment. The software is called BOLT. It means Biometry Open Language Tools, has a very special kind of meaning to the analysts in this field. And it's very generalized. It can do much more than this list here, but we designed it for organizations like you, where we can package easily a customized but turnkey analysis, meaning this analysis will meet the needs of specifically your data and your selection objectives, your breed's goals, in a in a customized way, but it's turnkey. In other words, so once it's set up, all you have to do is show the data at it, and out comes the answers, and you can do this very quickly on very large data sets on very low-cost computer hardware. Well, what kinds of things can we do? Here's a little illustration. One of the computations we have to do, it's called the M prime M computation. It's a specific for markers. Anyway, so for a typical data set, this, gosh, this was last year. I think it was 20,000 genotyped animals at 50,000 markers per animal. And then you have to impute, do all kinds of things. I think it was about 5 million animals. I estimated that it would be 6.6 quadrillion flops. And a flop is a floating point operation. It's multiply one number times another. And in order to do a single analysis, you'd have to do this computation, probably do it several times. And that would take 6.6 quadrillion multiplies, or it's multiplies and adds. Well, on this hardware, this very specialized hardware, it runs so fast, it can do 2.29 in this example. We're now up to 7 teraflops, all right? 7 teraflops a second, floating point operations per second. So this computation took 45 minutes to do this. That's what you can do with this kind of hardware. It's much, much faster than your conventional desktop PC. Oh, and by the way, that card, it just plugs into a PC. I'll show you a picture of it. And it's $1,000 is all it is. Okay, one of the steps in this computation is to solve it. So we take, in the case of Simmental, 15 million animals, 10 million performance observations, combine them all together in what we call the big mixed model equations, and then we solve it. And right now, that problem takes, Lauren, 24 hours, right, to solve the solve step. 48, yeah. So I did that for one prototype run. Here it was 51 million equations. So think birth weight, weaning weight, milk, and post-weaning gain, and all the other stuff that goes along with it for about 11 million animals. So we solved all that using our fastest non-GPU. So not using the GPU, our fastest time was 1,649.7 seconds. That's pretty fast compared to 24 or 48. But on the GPU, the very fastest program, software that we wrote, is that number at the bottom right corner, 76 seconds to solve that problem. 76 seconds. That's the kind of power these things have. That means that you could do that run every day or every hour in a day as new data comes in, and it wouldn't cost you anything. Another thing, so what that does is we said, well, it's not just about gaining speed. We can now apply new methods to it. And one of the new methods we've applied is this procedure called sampling methods, and I'll talk about why. And they take a lot longer than the conventional solve, assemble, and solve methods we've been using. But now that we have all this additional time, let's do something better with it, not just something faster. So why do samplers? There's no approximation in the accuracy. Right now, the accuracy values that come out of your existing analyses use approximation techniques, because accuracy is actually a lot harder to get than prediction error, or than predictions, than EPDs. This sampling method has no approximations when it estimates accuracy. But it also allows us to get prediction error covariance, which means we can now look at not only the accuracy of a bull to the population, but the accuracy between two alternative bulls, or two groups of bulls, or between different kinds of decisions that we're making. And that just is a byproduct of the computation. More importantly now, when we get into genomics, we can apply what are called marker selection methods. And I'll show you what that means. And then something one of our collaborators, Rohan Fernando, likes is you can put prior information in. So in these genomic evaluations, if someone already has some good estimates for certain things in the genomic analysis, you can plug those in instead of letting the data alone estimate them. And there's some advantages there, especially when you get into field data. All right, so what have we been able to do? Well, why hasn't anyone done this before? Well, it is very computationally intensive. And unless you do something on either a very expensive computer or in the GPU, the graphics processing units, it's just intractable. And I've had our colleagues, as recently as 2 years ago, say sampling methods will never be tractable. Well, all of us got together and worked out some math and some software to really improve these sampling methods and make them feasible. What you're looking at here is 3 different sized problems: small, medium, and large. They're all just subsets of Simmental. This last one is basically that last problem that we saw, and it's a little bigger version of it. It's 2 billion non-zero numbers that we have to deal with. And what we do is we take these numbers and sample the EPDs over and over again. We perturb them a little bit and resample them and resample them. And we'll do that instead of just solving them. We sample them with some variation. And that tells us what the accuracy is of these EPDs. We have to do this in our analysis. We're doing it 40,000 times. To do one complete sample in the conventional method for the largest data set takes almost 23 seconds. And if you have to do that 40,000 times, do the math, it's not tractable. You just can't do it routinely. Well, we rewrote the software and we got that speed. We got that down to 2 seconds per sample. And then we did some other tricks where we run things in more parallel. And we did make it tractable. So if you ever hear sampling methods aren't tractable, they are tractable. But that's another illustration of what this approach can do for you. So now let's move on to genomic evaluation. So sampling methods, that's a tweak. We get a much better accuracy value. I know a lot of you have seen problems with accuracy, especially on young animals. Those approximation techniques can cause some bias. This will remove that approximation bias by doing this method. But it also then gives us more power to squeeze more accuracy out of the predictions when there's genomic data in the analysis. It improves the accuracy of prediction by sampling for what are called marker effects. All right, to put that in perspective, right now there are 3 alternatives for how you perform a genomic evaluation. The top left here says GBLUP, and that's what you're doing right now. And that's a blending process where genotyped animals are predicted with their genotype data, and then everyone's predicted the conventional way with EPDs, and then an index uses it to blend them together. Well, there's a number of problems with that. It was the best that could be done at the time, but there's a lot of bias in that. There's a lot of bias just because, in large part, because genotyped animals tend to be only a very, very select group of animals and not a representation across the population. Well, Legara and Mistal and others developed some techniques. That's the second one down there, the single-step GBLUP, to allow all data, including the genomic animals, all to be predicted in the same evaluation. And that overcomes that bias when everything is predicted together. However, they used that in a way that didn't fully maximize that analysis, that method. The single-step GBLUP does not fully maximize the value of the genomic information that comes in. It does not squeeze every bit of accuracy out. And so Rohan Fernando and Dorian and Jack Deckers primarily developed what are called marker effects models, derivative of other people's work, but published on that. And we've published now 2 different variations of it, something called the hybrid model, which we originally proposed to implement and have implemented in prototype here. But now we've got a new technique that we just submitted the papers for that we've been using for the last 4 or 5 months called the super hybrid model. And it's an even better, faster way to implement this analysis that squeezes even more information, more accuracy out of the genomic data. And you'll hear us talk a lot about things like, we call it the Bayes alphabet. So these are just different ways to apply this hybrid or super hybrid marker effects model. That what it does is we pick a method that squeezes the most accuracy out of the genomic data in the shortest amount of time. here's an example of what we can do, and this is a real simple example. I took a total of 2.6 million pedigreed animals, 14,000, just under 14,000 were genotyped, and 2.5 million then were what's called imputed. Because they're related through pedigree, we can make predictions on all the other animals who are related to the genotyped animals on what their genetic makeup is from the marker data. And then we used about 2 million observations on birth weight to run this prototype. We ran it 3 ways. We ran it in a conventional BLUP. We ran it using an equivalent analogous method to that single-step GBLUP that's being implemented in other analyses. And then we ran it our way in what's one of these marker effects models, where it picks out which markers are effective. On the vertical axis here is the prediction error variance. So think of that's negatively correlated to accuracy. The higher the prediction error variance, the lower the accuracy in it. So the higher the line here is on the right, the less accurate the predictions are. The top line is conventional BLUP. And the horizontal axis here is I just took all the genotyped animals and divided them by their BLUP accuracy. So the highest accuracy animals are in the group on the left, and the lowest accuracy animals are in the group on the right. All right, everyone following. So you can see the, let's see if I can get there. The conventional BLUP line, this top line, you don't have a pointer, do you? The top line is the conventional BLUP line. That makes sense, right? These animals were divided by BLUP, and that shows you those are the least accurate predictions going all the way down to the very highest accuracy animals on the left. The middle line is this single step GBLUP kind of prediction where all the marker data is thrown in and it's basically used to calculate the covariance between animals. Nice little improvement in accuracy. Not little, pretty substantial, especially for these animals on the right. Those are the yearling animals. Those are the ones that we're trying to make selection decisions from most of the time. The bottom line, though, is the most accurate line, and that's using this marker effects model method, the super hybrid model, with a method that during this sampling process looks to pull out the markers that are actually having an effect. You know, we look at 50,000 markers, not every one of them will have an effect on birth weight. In fact, our estimates right now are out of 50,000 markers, maybe only 2,000 of them have an effect on birth weight. Now, other markers might have different effects on different traits, but for birth weight alone, there's only a handful. And so you want to estimate the effect of only that handful of markers, because that's more accurate than spreading this estimate across all 50,000 markers. And that is a substantial increase in accuracy that you gain just by applying a new computational technique, right? As opposed to going out and collecting more data. You get a big bump in accuracy by doing this sort of thing. And that's really why we wanted to implement these marker effects models, because they have this technique. They select out the markers that are important. Let me show you a quick result of what we're looking at. And this one I just drew this morning. We've been working on this one only for the last couple of days. So this is our newest data set. It's 6.1 million pedigreed animals, 4.8 million birth weight observations, and 1.9 million pedigree post-weaning gain observations. So it's 2 traits done simultaneously. 46,000 animals were genotyped now. That's what the data set's up to as of this weekend. For Simmental, we've got 46,000 genotyped animals at 50,000 SNP locations, 50,000 locations in the genome, of which 44,000 could actually be used in this analysis. What you're looking at here is on the horizontal axis is the prediction of what the marker, each marker's effect might be on birth weight, is probably on birth weight. And the vertical axis is then the prediction of that same marker's effect on post-weaning gain. So, right, so you can see through the middle here, there's a whole bunch of markers that affect both traits. And in this plot, there's about 200 of these markers that affect both traits. And those markers are actually pretty well known. Different studies up to this point have resolved most all of those markers pretty well. Warren Snelling's in here somewhere. He and I talked this morning. Other people have published on this. We've known that there are markers that affect birth weight, and there are markers that affect post-weaning gain, and we know that there are genes that affect both of them. But what I was really curious about is how many genes are at the zero axis, or how many markers representing linked to genes are at the zero axis. In other words, this line here is loci, markers of genes that affect only post-weaning gain. And the horizontal axis is genes that affect only birth weight, but not post-weaning gain. And it's neat to kind of sit and speculate what those genes might be. Genes that affect post-weaning gain but not birth weight might be genes involved with, I don't know, appetite or puberty or things like that. Disease resistance, and they wouldn't have an effect on birth weight necessarily. I was surprised at that. So genes that affect both traits, that's called a pleiotropic effect. They affect them both. Genes that don't affect both traits, that's the non-pleiotropic genes. Well, why is that important? So I took out of that larger set, I took the most important ones. These were the genes that I was, or the markers, not genes. These markers aren't necessarily on the genes, but they're close to them. I took out the most important ones, the ones that I was really pretty sure were right out of that plot, and just looked at them here, and I still got a lot of genes or markers on those 0 points. In other words, chromosomes, genes that affect only one trait or the other. Well, why is that important? Well, that explains why we can make genetic progress to decrease birth weight and still increase post-weaning gain, right? Does that make sense? There are a lot of genes out there that still impact only one or the other trait. And this is kind of the first real look that at least I've had at a very powerful data set. Remember, there's 46,000 genotyped animals and 6 million animals in the pedigree. This is the first look I've had. It just kind of how the genetics works, how the architecture actually works. It's starting to make sense, but it's very preliminary kind of result. But this is another thing we can do now with these models. So hybrid models, why are they important? Mostly because of this marker selection feature. They can go in and improve the accuracy by selecting out the markers that make the impact on the gene, and that improves the accuracy. Right now, we're running this in multiple components. We can do maternal effects, no problem. We do it multi-trait. That birth weight post-weaning gain was solved simultaneously, which is important because then that's how we get rid of the selection bias in post-weaning gain, solving it simultaneously. We can even have then different markers for different traits. I think you saw that. We also know that we can't describe all the genetic variation with the current set of markers because they aren't actually the genes, they're near the genes. So we fit this thing called an extra polygenic effect, and that's the amount of genetic effect that the markers can't describe. And that's a neat trick that Rohan and Dorian came up with in these analyses. What we propose then is to use what we're calling the MSRP approach. Anybody know what MSRP means? Anyone? Matti Sachi, reduced panel. Matti Sachi is sitting right down here. He's at Iowa State University, and he's the first one who I've seen has come up in beef cattle with identifying, a first attempt to identify which genes affect which traits, and he's done it for a large panel of traits. Well, we propose to take that approach where periodically, once a month or whatever makes sense as genomic data comes in, and look at all the markers again and say, any new markers coming in that are affecting traits that we didn't see before. And then for daily runs or weekly or whatever kind of run that your organization does, you just run the analysis on those markers, and that's exactly equivalent. It gives you the exact same accuracy gain rather than running all the markers every time looking for the ones. And we've been doing that now in prototype. Okay, so where are we at with the IGS analysis? We believe we've got proven superior marker effects models, this MEM, the super hybrid model. Clearly, we're gaining accuracy by implementing it. We've got a superior accuracy computation because we're using this sampling rather than just solving. So the accuracy computation is much, much more reliable. We've got a new stability approach. We've got a new breeds effects model. I don't have a lot of information here, but it's basically, it's really hard to get breed effects out of these complex breed association data sets. And so we're using basically the USDA mark breed effects and then compensating for genetic trends in those. Let's see, we've got, your analysis had a feature called heterogeneous variance in it. We've ripped that out. I can talk more about that with anyone who's interested in. And now Lauren Hyde is working on the prototype for solving all the carcass traits together simultaneously with the ultrasound. It's a more sensible analysis, and she includes birth weight in that evaluation to help add accuracy and remove bias. And then finally, we've got a new method for including external EPD information. You've always had a method. We just improved upon that, and we think it's a higher quality method. The status of the analysis, the software is ready. We've been prototyping like crazy. Data are nearly ready. You know, it's not easy putting these big data sets together on, and there's a lot of people working on that. That's not our space. And we're about to start what I'm calling the final acceptance process, and we've got an internal process before we release prototypes to the associations, and then each association is responsible for their internal process to review. But it's a feedback